Have a good one. All right, everyone. It's 2:30. Everyone, come on in. Find a seat. The more, the merrier. Okay, everyone. Let's get started. It's 2:30. How's everyone doing today? Second week is done. We're feeling good. We're feeling somewhere in the middle. Awesome. I'm so glad to hear. I love the energy. Let's keep that up for the whole time. So, my name is Kyle. I'm going to be your TA. Welcome to Math 1 T03, Calculus 1 for Engineering. A little bit about myself. I'm in my 4th year of Math and Computer Science, so I'm a student like you guys. I'm really interested in AI. I call myself an AI enthusiast. I worked at RBC for a co-op term in machine learning software engineering. I've also done a few research positions here at Master, so if you're curious about getting into that field, please feel free to ask me about that. We're going to get a little bit of admin stuff out of the way beforehand. First off, let's do it this way. Who has not seen the Teams page? Okay, you should look at the Teams page. In particular, there's a channel called the tutorial room. That's where everything that we need to do is going to be posted. So in particular, the blank notes are going to be posted there. Afterwards, the filled in notes and the video are going to be posted there as well. And I'll also post additional things there. What's important is there's an entry form as well. That form is going to help me get to know you guys a little bit better. I teach 2 tutorials back to back. Both of them have 500 students, but I still want to get to know each and every one of you. So if you can navigate to the Teams page, fill it out. I'll give you some important parts, but you don't have to do it right now. Some of the important things is, during the course, I'm going to try and include some of you guys in your fun facts in questions, so you'll see that today. So if you want to be in a question, fill out the form, tell me. I also like to bring candy to class. I have some with me today, so if you have any that you like, please let me know. With that admin stuff out of the way, I just want to answer your question really quick before we get started. No. So the blank notes will be posted probably 1 or 2 days before the tutorial. I'll try my best to plan as ahead as I can. Question. Okay, now I'm actually gonna welcome. Come on in, more the merrier. So, I'm gonna get started with a question that I was asked in the previous hour. Someone said, "What exactly is tutorial?" So who's wondering that right now? Hands high. It's okay. So I'm wondering that too. So let's talk about that together. I'm gonna give a little example. This is not related to calculus, but we're gonna discuss it together. And hopefully this will be a good example of what tutorial is like. If you saw this before, just let's keep that as a secret between you and me, okay? So my question is, example, okay, what is this huge number on the left times that huge number on the right? Okay, who knows the answer to that right away? I know you don't. Who has not been here before and does not know the answer? Yeah. Oh, you have no idea? Exactly. What makes this problem difficult? What makes this problem difficult? Huge numbers, right? Huge numbers, we're trying to multiply them. We could put it in our calculator, but we won't even be able to get an answer because the numbers are too high. Rounding errors, right? So what I'm going to do is I'm going to pose to you a different question. I'm going to pick on you. What's your name?
Hi, Owen.
Owen. Good to meet you, Owen. So Owen, I have a second question for you. What is 26 plus 20? 46. Who also got 46? Okay, that's good. I'm glad. I wasn't sure. Okay. What makes this second problem easier than the first one? Smaller numbers. We've worked with them before. We know how to add numbers, but maybe not how to multiply those large ones, right? I'm going to tell you something really quick. What if I tell you, so does it make it easier if I tell you that this first number is 3 to the power of 26, and this second number is 3 to the power of 20? So now, Owen, what's the answer to the to the first question? Or anyone, what's the answer to the first question? Yeah. 3 to the power of 46. What's the moral of this story here? The moral is try and simplify some of those problems into problems that look just a little bit easier. How does that sound? Awesome. Now with that out of the way, let's get into some calculus here. So let's talk about inverse functions. Also, I forgot to remove these ones. So these ones are the same or similar to other ones we're going to do, so let's just call these ones homework. One piece of feedback I've got is that everyone wants to see more practice problems, right? More things just to study. So anytime we don't cover a question, you can use that as just an extra homework problem. I'll always try and put more than we have time for. Okay, let's get started with this first example. So Leslie can swim 400 meters in 8.5 minutes. Is Leslie here? Oh, that's you. Okay, how's it going? Do you want a Tootsie Pop? Yes? So Leslie can swim 400 meters in 8.5 minutes. During a swimming drill, we're going to let f be the function t cubed plus 2e to the t plus 1. And that function is going to represent the distance away from the pool at time t. Okay, so we're going to do two things. We're going to find the time at which Leslie is 3 meters away from the edge of the pool, and in that case, that is, what is f inverse at 3? And we're also going to find f inverse at f at 2. Let's start with the first example. So remember, finding an inverse function, right? Normally a function maps our inputs to our outputs, but it's also equally valuable to ask what input will cause a given output. So this question is equal to saying, what value of t causes f at t to be equal to 3? Okay. This problem should look similar to some of your child's math problems, your assignment problems for this week, right? Did anyone try doing what you did in high school? So you set f equal to y, and then you try and isolate for y. Has anyone tried that? Okay. Everyone hands high and you try it. Okay. Keep your hands up if it worked. Okay. This is the trick. I feel bad that this happened so early in this course. So unfortunately, you cannot solve this type of problem using that approach in high school. The reason why is because some functions do not have what we call elementary inverses. In particular, when we have this sum of this polynomial, so we have a sum of t cubed plus 2e to the t, it's not possible to write its inverse in terms of functions we're using. The good thing is we don't have to. We're not looking for an inverse over the entire domain. We're looking for an inverse of this function just in one place. In particular, we're looking for f of t is equal to 3. So that's the first thing we should know. The second thing we should know is that we have this t cubed, which behaves nicely when our t's are nice, right? But we have 2e to the t. That most of the time is going to spit out decimals, right? Except for, right, e to the t will spit out decimals except when t is the log of something, right? So what we need is a number that's going to look nice enough, right? So the e to the t is going to be decimally except, so it's going to have decimals, except when t is a log of something. And this t cubed is going to be nice, it's going to be nice when we have nice inputs. So we know in order for our output to be an integer, right? In order for our output to be 3, we need both of these terms to be nice. So we know we need a logarithm to satisfy the e of t being nice. We need a not logarithm for the t cubed to be nice. Let's just try and pick a number that makes e to the t nice, right? Nice enough. So what's the value of t that would make e to the t nice? 0. Let's just try 0. So if we plug in f at 0, that's going to give us 0 cubed plus 2e to the 0 plus 1. E to the 0, that's just 1, so we have 2 plus 1 is 3. Aha! We solved it. We found the answer. We found a number, t, which when plugged in gives us f of t is equal to 3. Who feels unsatisfied by this? bad. This feels like we just landed on it. We stumbled upon it by trial and error, right? So there are other tricks that we can do to see that this, to see why this works. We'll show another example here with some trig functions in a sec as well. The other thing to know is that we need to know when our function has an inverse, right? So from high school, we remember functions have an inverse if it passes the horizontal line, right? So we know our t cubed, that's going to pass the horizontal line test. Our e to the t is going to pass the horizontal line test. And since we know that, we'll also see later in the course that in order for that to happen, they can't cross each other's values, right? We can't cross any of the horizontal lines over again. So if you were to try one number as too small, you could move further along one direction or the other. Eventually, you'll land up here. And we'll cover more of that kind of intermediate stuff later on. So that's just kind of like a hint of what was. Anyway, what were you going to ask? I'm sorry? Where can you find the notes? That's going to be on the teaching page. Oh, you can't open it. Everyone take 30 seconds. Yeah, okay. Who's not able to find the notes? Okay. Here's what I'm gonna do. I'm gonna put the next question on. This one's for you to try. We'll reconvene in 2 minutes, and I'm gonna look at some of the other team pages. So everyone talk with your neighbor for 2 minutes. So. Everyone, the notes are not in the file section, they're in the post. You have to look in the tutorial room post. Yes. I'm sorry? Okay. Yes, question. Everything will be posted at the end. Okay, let's talk about this together. Let's do this together. So, yeah, let's do it. Did anyone get an answer for A? Just shout it out. Zero. We can, one more time. I didn't hear you guys. What's the answer for A? 0. That's a bit better. 6 pi. Very good. And then, what about B? Did anyone get an answer for B? Oh, did I skip the... Did I skip B in this one? Oh, I did skip B in this one. Sorry, guys. We're gonna go back. I totally forgot. So, we're gonna do B in this first one, and then we can talk about B together. So, in particular, functions map inputs to outputs, and their inverses map outputs to inputs. So, when we're finding f inverse at f over 2, what we're saying is, okay, remember, t is our time, and f is our distance away, right? So we're saying, at what time are we the distance away that we are at when the time is 2? So we're answering our own question when we ask the question, right? So I'll say it one more time. When we say f inverse of f over 2, we're saying, what is our time that the distance we're at when the time is 2? I know that sounds jumbled, but in particular, we can take, when we have inverse of a function applied after the function, they can cancel. So our f inverse and our f cancel. And that gives us 2. Yeah?
For part A, what do you do if plugging in 0 what steps do you take to the final?
The question was, in part A, what happens if the number that you plug in doesn't give us the correct answer? What if we plug in 0 and it doesn't give us the correct answer? What you might want to try are other numbers that make each of the t nice and also our t cubes nice. In particular, I think 0 is the only answer that I can think of that even works. And most of the time, because you can't find an inverse written in elementary functions, most of the time the intuitive answer will be the one I want. By the way, let me just ask, how's my volume? Can anyone not hear me? It's good? Oh, in the back it's good? That's great. I'm glad to hear. Okay, so let's just quickly do number 2. I know we said that we were trying it on our own, but we need something here. So notice we're adding a sine of x and an x squared, and we want to find when this whole function is equal to 2. We'll notice when we plug in things into sine x, it almost always gives us decimally numbers. It's only when we have multiples of pi over 2 where our sine function is nice, right? If we plug in a multiple of pi over 2, we're going to get either 1 or negative 1 or 0, depending on what multiple it is, right? Does that make sense? So when we plug in values into pi over, or into sine of x, multiples of pi over 2 are nice. Are integers. Okay, the problem is if we plug in a multiple of pi over 2 into our x squared, there's going to be lots of decimals. Because we're squaring the number pi. Is there a multiple of pi over 2 such that sine is nice, but also x squared is nice? Is there a multiple? What multiple would it be? Sorry? 0 of them. 0, right? If we have 0 copies of pi over 2, that makes sine of 0, 0, and it makes 0 squared 0. So let's try plugging in g at 0. That'll give us 2 cosine of 0 plus the sine of 0 plus 0 squared, which gives us 2, which is exactly what we were looking for. Also, the second question we can answer by doing a similar trick as before. Our g inverse will cancel with our g. The value will be just pi over 2. What one should do is also check that the domain of our function is correct. So in particular, we're taking pi over 2, which falls within our outputs for our cosine and our sine, but so for now we can gloss over that. Yes? Yeah, exactly. So in general, what you might have to do is check to make sure that our function application is valid, right? So when we take g of pi over 2, we want to make sure that when we take the inverse, it's going to be within its range, right? So for example, the reason why I'm going to give this, why this is an important example is, I'm just going to illustrate this. If we do sine of arcsine of 2, and if we do arcsine of sine of 2, only one of these is valid, right? So in particular, if we do this, this is allowed, because arcsine, so the inputs to arcsine, must be within the interval -1 to 1. Actually, I'm not sure about the ends. So this expression does not make sense, but this expression does. And this will not give us 2 back. It will give us something else. But the point is, you should verify this for our g case as well. So maybe we should do that together, actually. So g of pi over 2. Actually, Is this fine? No, actually we should verify. This is 2 times the cosine of pi over 2 plus the sine of pi over 2 plus pi over 2 squared. So this cosine of pi over 2 is going to be 0. Sine of pi over 2 is 1, so we have 1 plus pi over 2 squared. And then if we were to take the inverse of this, yeah, this should be fine. Let's just gloss over this for now. I don't think you're going to be asked, just in general, you can just assume that if you're going to get this inverse, you're going to be fine. I don't think this is going to be a detail that's going to be covered very much, especially because the answers are going to be multiple choice. But let's keep going, and we can fill in the details later. Okay, right-angled trigonometry. So this is going to be similar to a question that we found on child math. Has anyone tried plugging this value just straight into your calculator? Yeah, hand high. Who put this into your calculator and then put that as the answer? Did that work? Okay. So the reason why is because we want to say the exact value of tan of arc sine of 1 over 6. Oh, before we keep going, who doesn't know what arc sine means? It's okay. Hand high. Okay, sorry, that's my fault. So, is everyone familiar with this if we write the sine inverse? Does everyone know what that means? It's like the inverse sine function? Yeah. So arc sine is just the exact same. We're going to call our inverse sine arc sine. And you're probably wondering, okay, Kyle, why are you doing this? Just to confuse us more? No. Because a lot of the time when we use negative powers, we need to reciprocate. Some people, like sometimes they can just be confusing because the inverse sine is not the same thing as 1 over sine. So we're going to call all of our inverse trigs arc that. Does that make sense? Good. Thank you for the thumbs up. Okay, so let's compute this exact value here. So in particular, we talked about mapping inputs to outputs and outputs to inputs. So sine takes an angle and spits out a distance, right? Or opposite over hypotenuse. That means our inverse side is going to take a ratio of distances and output an angle. So arc sine of 1 over 6, that's just going to be an angle. Let's call it theta. So let's let theta be the arc sine of 1 over 6. Let's take the sine on both sides. So sine of theta is going to be the sine of the arc sine of 1 over 6. 1 over 6 is between negative 1 and 1. So that's in our domain. So it's going to cancel. So we have sine of arc sine, that's just going to go away. So sine of theta is 1 over 6. From here, remember, that's equal to our opposite side over our hypotenuse. So let's draw a right-angled triangle here. We'll let theta here be our angle. Our opposite side is going to be 1, and our hypotenuse is going to be 6. Yeah, question? I'm sorry? Where's the tangent? We're getting there. Very good question. So from here, does anyone remember what is the tangent of this angle? What's that going to be equal to? Yeah. The opposite side over the adjacent side. So here this is adjacent. We know our tangent of our angle is going to be equal to, let's do this here. Tangent of our angle is our opposite over our adjacent. What is our adjacent? Well, we need to use Pythagorean theorem to find it. So remember, our Pythagorean theorem says that our adjacent squared plus 1 squared is equal to 6 squared. So, in particular, our adjacent is going to be equal to 36 minus 1 all rooted. root of 35. So let's sub this into our tangent formula. So this is going to be, our opposite side is 1, and our adjacent is root 35. Okay, let's take a pause. Let's take a pause. What questions do we have? Is this all good? Oh, yes. Yes, so in order for us to take an outside of a number, it has to be less than 1, and it has to be bigger than negative, right? Because we know the outputs of sine are at max 1 or negative 1. Anyway, this is not a detail I think will be very important for the purposes of this course. Sorry about that. Yes. Should you rationalize the denominator? We got the same question before. You don't have to worry about this for now. Remember, all your tests are going to be multiple choice. So you won't get a mark off if you don't rationalize the denominator unless all of the answers have the denominator rationalized. What other questions do we have? Yes? Yeah, sorry? What if theta is an obtuse angle? So, I'm not sure. I don't think, I'm not sure I understand. So here we have a right angle triangle. If there was any obtuse angle, it would be a right angle triangle, right? Then the angles would add up to more than 180. Yes? Yeah, I'm sorry? So, let's see. So arc sine is a, no. No, there should be only one value here. It's only going to be one thing because we're taking functions on functions. If they were, this is different than asking. So remember, arc sine is a function which maps inputs to outputs, right? There's only going to be one output for each input. Same as tangent, right? So if we have this positive input 1 over 6, we're going to get a positive output. Yeah. Yeah. So, well, tangent works for all inputs, right? Except for multiples of multiples of pi. On multiples of pi, is that right? Before pi was 6. Anyway, we're away from any discontinuity. We can't take any input except for points where the denominator comes from. Yes. I'm sorry? If we had a which? Another? Square root 2 over 2 inside of the arc sine?
No, we have exactly square root 2 instead of 1 over 6. Instead of making a triangle, we should put it in.
If you have a solution that works, that's okay. But this is for the context of our assignments in child time. Okay, let's all reconvene. I think we should all reconvene here. So, let's move on to the next question. We've just got a few more things that we want to cover. So, okay. I'm going to jump ahead in the notes. I put the same question twice, so we're going to do this one, and we'll go back up in a second. So Harry and Ian, are either of you here? I didn't ask before if, yeah. Maybe not. Okay, so Harry and Ian both like to play basketball. Harry scores 10 to the x points. Ian scores 2e to the x points. And we're also told that they got the same number of points in the game. So the question says, what is x? So in other words, let's solve the equation 10 to the x is equal to 2e to the x. Now part A says let's solve it using both the natural and the common logs. That's going to take too much time. So we're just going to solve it using the natural log, and the other part can be homework. So what we're going to do is we're going to take the log on both sides. So we have ln of 10 to the power of x is equal to the ln of 2e to the x. Now from our power rule, remember we know that the power can come down and be a multiple in front of a log. So this is the same thing as x ln of 10. On the right, we're going to use our product rule. So our product rule says that if we take the ln of a product, that's equal to the sum of the lns. So this is the same thing as ln of 2 plus the ln of e to the x. Now, if we simplify the right side a little bit more, remember that a logarithm is the inverse of an exponential function. We've been talking about inverses, they cancel. So the log of our e to the x, that's just going to be equal to x. So the ln of 2 is equal to x, or the ln of e to the x is equal to x. So we have x ln of 10 is equal to ln of 2 plus x. What we're going to do is move all of our x's to one side now. So we have x ln of 10 minus x is equal to the ln of 2. Since we have x's in the base in multiple terms, we can factor our x. So we'll take a factor of x out. We'll have x is equal to the ln of 10, or sorry, x times the ln of 10 minus 1 is the ln of 2. And we can now divide by this constant, divide by that multiple there. So x is equal to the ln of 2 divided by the ln of 10 minus 1. And that's our final answer. What questions do we have about that one? How's my pace, by the way? Oh, yeah, question. Yeah. If there was start, there was no fun. So whenever okay, the question was how do we know what the log is applying to? The log takes higher precedence in the order of operation. So this, whenever I write ln of something, that just means ln with invisible brackets here. Yeah, good question. Okay, let's go back up a little bit. We're going to solve this exponential equation here. So we're going to solve the equation 3 to the power of x minus 1 plus 3 to the x is equal to 36. Okay, so the thing that made the last problem difficult was that the bases were different. The thing that makes this problem difficult is that the exponents are different. The good thing is we know how to work with the exponents. So in particular, our 3 to the x, let's decompose that. That's the same thing as being, we'll write the 3 to the x, that's the same as 3 times 3 to the x minus 1. Is everyone okay with that? So if we were to try and work in reverse, if we multiply 3 times 3 to the x minus 1, we add those powers. So 3 to the 1, and we add 3 to the, so we add x minus 1, 1 minus 1 plus x, that's just x. So we'll decompose our x, our 3 to the x, we'll decompose that as 3 times 3 to the x minus 1. We'll factor out our 3 to the x minus 1. So we'll factor that out. We have 1 plus 3. Let's take a quick pause. I'm hearing some murmuring. What questions do we have? Yes? Where did the other 3 come from? So when we moved from the first line to the second line, what we did was we factored, right? So we have an invisible 1 here. That comes from here. And then this 3 went down there. Does that answer your question? So we turned our 3 to the power of x into 3 times 3 to the x minus 1. So we broke it down like this. And remember, when you add things, you add their exponents. So this is like a 3 to the 1. So if we were to multiply those together, that gets the same thing back. Does that make sense? We have 3 to the 1 times 3 to the x minus 1. That's 3. Yes? So here. Let's talk about it. Okay. From here, we have 4 times 3 to the x minus 1. Let's divide both sides by 4. So we have 3 to the x minus 1 is equal to 9. So 9 is just the same thing as 3 squared. So let's compare those exponents. We know x minus 1 is equal to 2. So that tells us x is equal to 3. Is everyone okay with that example? What questions do we have? Yes? Yeah, that's a good question. This is the main approach that comes to mind. There also are other equivalent solutions if you multiply and divide by the base. If you have another solution that works for you, please feel free to use it. Yeah. There's still a lot of room. What questions do we have? Yeah. Would it be easier if we just use log? So the difficulty is if we're going to take the log on both sides, we have log of a sum. So we don't have much to do with that. So the question was, why can't we just use logarithms? If we took the log of the original equation, we have the logarithm of a sum. We don't have any rules to deal with that. Yes. Yes, that's equivalent. Okay, let's keep moving. There's some more stuff that we've got to get to. So let's go to. We're going to do some trig identities here. Is everyone okay with that? No trig? Yeah, good for trig? So we're going to skip these two. Actually, there's a lot. This one's similar to your child's math, but I did this in the first tutorial, so actually maybe I'll do these ones and then we can compare. You can compare them afterwards. Is that a good idea? I'll post both notes. Let's do this one really quick. So let's prove this trigonometric identity. So we'll start on the left side here. We have sine of x divided by 1 minus cosine of x, and then we're adding sine of x divided by 1 plus cosine of x. When we have these two fractions with different denominators, one thing that we might want to do is try and find a common denominator. So in particular, let's multiply the left fraction by 1 plus cos of x. And let's multiply the second fraction by 1 minus cos of x. So on the left side, we're going to get sine of x times 1 plus cosine of x over 1 minus cos of x, 1 plus cosine of x. And on the right, we'll get sine of x times 1 minus cos of x over 1 plus cosine of x times 1 minus cosine of x. How's my speed? Sorry, am I moving a little bit too quickly? Yeah? Sorry. I'm going to try and slow down a little bit. So from here, our denominators are equal. And also, we can rewrite our denominators by expanding out. We have a type of factor here. This is a difference of squares. So we can rewrite this. Our denominator is going to turn into 1 minus the cosine of x squared. Our numerator, let's factor that out. Or sorry, let's expand that out. So we have sine of x plus sine of x cosine of x. And then on the right, we'll have sine of x minus sine of x times cosine of x. I'm missing an x here, sorry, in the numerator. So these two terms are equivalent, the sine of x minus sine of x. So those two are going to go away. So here we're left with in the numerator 2 sine of x. And in the denominator we have 1 minus cosine squared of x. Does anyone know what that denominator is equal to? Sine squared of x. So we have 2 sine of x divided by sine squared of x. So one of those copies are going to go away. We'll have 2 over sine of x, which is equal to 2 times the cos. 2 times the cosecant of x. Okay. Is everyone okay with this example? Thank you. Yes, question. We did the waterfall sign? We found a common denominator. When you add fractions, you find a common denominator. No, finding common denominator is just expression. But I think you're thinking like yes, what question do we have over here? The question was, how many trig identities should you remember? So I'm going to answer this with not an exact number because I don't think there's a number of, well, I guess ideally as many trig identities as you can remember, but our tests are going to be all multiple choice. So you won't have to do a proof like this in class or for a test. All right, I feel like we're losing some people. I forgot I was going to give out some candy earlier. So what I'm going to do is just have people on the end just grab a handful and pass them down the road. I forgot to do that earlier. And then once you get to the top, just pass them down the other row. If you're too far away, just get it after. Let's quiet down. We have just another 7 minutes. Hold on, everyone. I'm just gonna take 7 minutes of your time, and then we'll go for the weekend. Okay? So. Let's look at functions. We'll look at functions and their graphs. So in particular, here's an example. Let's find the domain of this function f, which is equal to the logarithm of 18 minus the square root of x plus 7. Okay, so how do we solve this one? In particular, we know the logarithm can only take positive inputs. So we know the inside of the logarithm must be greater than 0. So we know 18 minus the square root of x plus 7 is greater than 0. We can continue to solve this inequality by adding root of x plus 7 to both sides. So we have 18 greater than root of x plus 7. We can square both sides. So 18 squared, anyone know that? 324. I got it wrong in the first tutorial, which is pretty funny. So is x greater than x plus 7? And then in particular, we have x is going to be less than 317. Okay. So are we done? Who thinks we're done? I thought we were done. Why aren't we done? Yeah. Shout, shout, shout. Yes, we have to make sure our input to the root is positive, or actually greater than 0, greater than or equal to 0. So this root has to be greater than or equal to 0. So let's solve this inequality too. We have x plus 7 greater than or equal to 0. So x has to be greater than or equal to -7. So our final solution is x has to be between -7 and 317. If you can pass it back this way, just to the other side. Pass it back this way, yeah. You can grab one though, but just pass the bag. Okay. Okay. Let's do one more. Okay, everyone? Oh, yes, question. Okay, very good. Okay, so this is an important distinction. So the question was, why did we put greater or equal to on the root side, but we only put strictly greater than for the logarithm? So the reason why is because you can take the square root of 0, but you can't take the logarithm of 0. So that's why the logarithm has to be a strict inequality. The square root it doesn't have to be strict. Can you pass the bag? Not very nice. Sorry, guys. If you just want to take some off the side, I'm sorry. I'll try and get more. There's 1,000 of you guys. Okay. So, let's do one more. 3 more minutes. So, okay. Everyone, please, let's just finish up. If you pack up early, it's just a little bit disruptive, especially if you go through the rows. So, let's find the inverse of this function. I know we talked earlier about how it's difficult to find inverses of a lot of functions. This is a function where we are able to find the inverse. Okay? The way we're going to do that is by doing a clever rewrite. So what's difficult about this one is we have the x in 2 different places. What we're going to do is we're going to try and find a way we can write it so there's only an x in one place. We know we can multiply fractions by, we can multiply the numerator and the denominator by the same thing. We can also divide the numerator and denominator by the same thing. So let's multiply, or we'll divide the numerator and denominator by 1 over e to the x. So we'll divide by 1 over e to the x on both the numerator and the denominator. So f can be rewritten as 8 minus 2 e to the negative x over 3. So if we set that equal to y, what we can do is now let's just isolate for x. So we'll multiply both sides by 3. 3y is equal to 8 minus 2 e to the negative x. We'll subtract 8 from both sides. So 3y is minus 8 is equal to negative 2 e to the negative x. We'll divide both sides by negative 2. So e to the negative x is equal to 3y minus 8 over negative 2. We'll take the log on both sides. So negative x is equal to the log of 3y minus 8 over negative 2. For anyone writing on pencil paper, sorry, I know that hasn't gotten the copy-paste update yet. And then thus x is negative log of that value there. Okay, so it is 3:20. Thank you very much for coming. Sorry there's not very much candy left. Have a great weekend, and we'll see you here next Friday when we're going to talk about limits.
What's the difficulty for the midterm and the final?
Okay, that's a good question. So there was just a question that was asked, which was, are all the questions going to be this easy? What I'll say is, first off, a lot of these questions are not easy, especially if you haven't seen them before. The second thing is, we should try and do all of the questions even if you have seen them before. The reason why is because even though you've seen a lot of the derivative stuff at the beginning of the course, there's going to be a point where we hit integration and it's all going to get a lot more challenging. So do all of the questions, do all the practice, and study properly. So we build upon. Sorry?
All of them will be MCQ.
Yes, but we should continue to develop our skills by doing all of the questions properly. Okay, thank you.
I have a question.
Thank you. Yes.
So in the practice assignment, in trigonometry, the last question, I think there's 2 answers. I think -3 also works.
So if you put in, if you put in -3, oh yeah, cos is an odd, oh yeah, cos is, both are even, yeah.
Yeah.
Okay, very good.
But the answer is only 3.
Well, -3 also works too. It should be fine. Thank you. Oh, sorry. I think we're waiting on this side. Sorry, you first.